Hey there, RISD 5th grade teachers. Welcome to this explainer mapping out your very first unit of the year, Onward We Go. I am super excited to walk you through this material because, well, this unit is really all about setting our kids up for a successful, safe, and honestly, a really engaging year of science. We aren't just teaching facts here, we're literally building little scientists and engineers.
To get there, here is our agenda. We're going to cover 1. Unit Teaks and Mastery, 2. Core Science Concepts, 3. Common Misconceptions, 4. Investigations and Mods, and 5. Vocabulary and the word wall. Let's dive in.
Let's kick things off with Section 1, Unit Teaks and Mastery. What to master?
Now, this unit hits several priority teaks, but they're uniquely focused on how we actually do science. You'll be focusing heavily on foundational scientific practices, introducing the claim, evidence, reasoning, or CER framework, analyzing the advantages and limitations of models, and bringing in environmental impacts through natural resource conservation. Basically, you're laying down the tracks that the rest of the year's science content is going to run on. So, what does mastery actually look like here? Well, true mastery in Unit 1 isn't just about a student memorizing some facts for a test. It's really about behavior. It's about students safely conducting investigations in the classroom, knowing how to properly set up and organize data in their science notebooks, and, this is a big one, respectfully arguing their scientific claims with their peers. If they can do all that, boom, you've won.
Moving right along to Section 2, Core Science Concepts, Foundational Knowledge.
The absolute crucial foundation to lay in this unit is distinguishing between two different types of investigations. First up, we've got experimental investigations. These are your classic fair tests with a control and variables that you change to test a hypothesis. Then, we have descriptive investigations. This is where students simply observe phenomena in action and draw conclusions from what they see, without actually tweaking any variables themselves. Both are totally valid science, but the kids definitely need to know the difference. And this cycle right here brilliantly illustrates the continuous investigation loop we want our students to internalize. Because science isn't just a straight line, right? It's a loop. We want them asking questions, planning what tools they need, conducting the steps, recording observations, communicating their results, and then repeating the whole process. Good science always leaves you with more questions.
Now, when we do get into those experimental investigations, you absolutely must emphasize to your class why we only test one independent variable at a time. It's so important. If more than one variable changes at the same time, well, the experiment is no longer valid. You literally can't tell which variable actually caused the change in the results. Keeping it to one independent variable ensures a totally fair and valid scientific test. Next up is Section 3, Common Misconceptions, Spotting Them Early. So, the first major misconception involves scientific models. Students, and let's be real, sometimes adults too, often think that if a model has a limitation, it means the model is just bad or a complete failure. We need to correct this right out of the gate by teaching that limitations are simply the boundaries of that model. Like a paper airplane is an awesome model of flight, right? But its limitation is that it doesn't have an engine. That doesn't make it a bad model. It just defines what it can and cannot show us.
Speaking of airplanes, during the upcoming Paper Airplane Lab on Day 5, kids often just assume that more folds in the nose automatically equals a farther flight. And when their highly folded plane inevitably nosedives right into the floor, they think they failed. You really have to reinforce that the data tells the story, even if their initial hypothesis is totally unsupported. An unsupported hypothesis is still incredibly valuable scientific data.
Finally, kids constantly confuse their variables. It just happens. When they do, give them this super simple, surefire trick to remember. The independent variable is what you change on purpose. The dependent variable is what you measure. Honestly, if you drill that in early, it's going to pay off massive dividends all year long.
All right, Section 4, Investigations and Mods, Classroom Application.
For the main experimental investigation, your students are going to become aerospace engineers. They'll build 3 identical base airplanes, but they're going to change only the number of nose folds, doing 2, 4, and 6 folds. They'll conduct 3 trials for each plane, and they absolutely must use a consistent thrower to keep the force controlled. Then, they'll measure the distance flown in centimeters and calculate the averages. It is incredibly hands-on, high-energy science.
Now, to set everyone up for success, preparation is absolutely key. Do yourself a favor and pre-tape launch lines on the floor before class. It will save you from so much chaos. For students who might struggle with math or organization, go ahead and provide partially completed data tables with one row already filled in. And heavily support your emergent bilingual students by pairing them with bilingual bridge partners and letting them brainstorm and write hypotheses in their home language first before translating to English.
A bit later in the unit, there's also this fantastic non-digital conservation lab. To hit our conservation teaks early, students will act as engineers tracking their own daily routines, morning, afternoon, and evening, to pinpoint exactly where they waste natural resources. Then, using the engineering design process, they'll brainstorm real-world solutions. Things like turning off the water while brushing their teeth, and they'll sketch out a plan. It's just so relevant to their everyday lives.
And our final stop, Section 5, Vocabulary and Word Wall. Total physical response.
You'll introduce foundational terms like hypothesis, variable, and control during your interactive read-alouds using the provided slide decks. Just a quick pro tip, make sure you build the frame for the word wall before day 1, so it's ready to grow as you introduce these terms one by one.
To really lock this vocabulary in, you are going to use total physical response. Deliver this interactive word wall script exactly like this in class. When you define variable, have all the students wave their hands around to physically show change. And when you define control, have them hold their arms perfectly rigidly still. Connecting that physical movement to the academic word is an absolute game changer for retention.
Next up, when teaching about scientific models on day 6, you'll add the words advantage, criteria, and limitation to the word wall.
And again, you're going to use this physical script for these terms. When you define advantage as a characteristic of a model that is useful, everyone gives a huge thumbs up. For limitation, which is the boundary of a model, everyone gives a thumbs down. Simple, but highly effective.
You'll wrap up your word wall additions with environmental terms during the conservation lessons. Make sure to explicitly highlight Spanish cognates here. Point out that conservation is conservación and impact is impacto. It's a brilliant, simple way to bridge academic vocabulary for your emergent bilinguals and really validate their home language in your science classroom.
Threaded throughout all this vocabulary, and honestly throughout the entire year, is the CER framework: claim, evidence, and reasoning. They are going to practice this extensively. In fact, you'll introduce it with a super fun video on day 3 where they have to use evidence to determine if a dad in a commercial is actually an alien. They'll learn that a claim answers the question, evidence is the data or observations, and reasoning explains how that evidence actually supports the claim.
And that brings us to the end of our unit. You'll wrap up by challenging your students with this essential question: how has space travel impacted science and society? So you have the roadmap, you know the misconceptions to watch out for, and you have the tools to engage every single learner. But the ultimate question remains for you as the teacher: how will you use this incredible foundation to inspire the next generation of scientists and engineers in your classroom?